Let's take a look at some double displacement reactions, specifically precipitation type reactions. So we're going to take a look at the overall equation, which is AB plus CD yields AD plus CB. The way to go about predicting your products is to follow this sort of outside-inside rule. So what ends up happening is the outside components of each compound hook up, and then the inside. You always want the cation of the compounds to be the first part of the new compounds. So that's why it's really important over here that you write C before the B, because this is the cation and it has to be written first. So let's take a look at our first example, lead 2 nitrate with potassium iodide. When we go to hook up the outside and inside, we get the names of our new compounds. So in this case, we are going to create lead 2 iodide, and you keep the same valence for lead that was made in the first compound for the second compound. So we wouldn't just switch to lead 4 at this point. So let's finish the word equation. So we would get lead 2 iodide plus potassium nitrate. Okay. When we want to take this word equation and put it into a molecular equation, we need to know the formulas for each of these compounds. So what we're going to do is we're going to look at the periodic table for valences and also our polyatomic multivalent ions. When we take a look at lead 2 nitrate, Pb, they're asking us to pick a valence of 2. Nitrate is NO3, which has a valence of 1. When we do our crisscross, we're going to put nitrate in brackets, and the 2 is going to come down. I'm going to put a little AQ here, meaning that we're going to make it aqueous, dissolved in solution, because in order for these ions to swap partners, they have to be dissolved in solution. They can't be solids. Next, we're going to react that with some potassium iodide. Potassium has a valence of 1. Iodine has a valence of -1. When we crisscross, we just get Ki. Now, what are the products we've already established are going to be lead 2 iodide and potassium nitrate? Let's take a look at that in terms of the ions that are created in solution. So here I've got a visual for us. When we take lead 2 iodide and we dissolve it in solution, you have mobile ions floating around. You have lead 2 ions and nitrate ions. And what I've done is I've sort of looked at the ratio. So for every one of these, you get 1 lead and you get 2 nitrate. So I tried to depict that within the beaker. Over here, we have aqueous potassium iodide. So you have some potassium ions floating around with their charge, and you have some iodide ions floating around. Remember that iodide, this is an ion, not a diatomic molecule. Ions are different than diatomic molecules. So you might confuse that with one of your Hofbrinkels, but as an ion, it is not diatomic. So if we were to add those ions together in solution, let's take a look. We now have them all floating around in the same beaker. Well, what's going to happen is some of these ions are going to hook up to form new compounds, as we just saw. Lead 2 nitrate, potassium iodide, we swap partners. So what ends up happening is potassium hooks up with the nitrate in solution, and the lead hooks up with the iodide in solution. Lead 2 iodide forms a solid in solution. And what will happen is it will then start to settle towards the bottom of the beaker. So that's how we get a precipitate, the ions coming together. Now, how did I know that that was the solid that was going to form? What you must do is you must consult what is referred to as a solubility table. So what I'm going to do is I'm going to take a look at the 2 compounds that are formed. The 2 compounds that are formed are lead 2 iodide. So I'm going to go find that on the solubility table. Here's lead 2 and here's iodide. Because the solubility tells me that there's an S, meaning there's a solid that forms, that means that that is your precipitate. S for solid. Let's just take a look at the other product just to be sure. So let's take a look at potassium nitrate. Here's potassium, and if I go across and I stop at nitrate, which is up here, and I see it says AQ, meaning it stays aqueous in solution. Perfect. So we now know that the lead 2 iodide is our precipitate. Let's go take a look at what this reaction looks like in terms of a demonstration. Okay, now that we're back, let's just finish off our molecular equation here. So we know that lead 2 iodide is formed, and that is our solid. So we're going to write that as S, S for solid. And we know that potassium nitrate is also formed, but that remains as aqueous. So we have completed this, but we now must balance the equation. So I see that I have one lead, one iodide, 1 or 2 here, so we must put a 2 in front here. We have 2 nitrogen here, only 1 here. I have to fix that, and everything else is balanced. When we do what's referred to as an ionic equation, just as I showed you with those beakers, we're going to break each of these compounds into their respective ions. So lead has a charge of +2, and we write AQ, meaning it's in its aqueous form. We have 2 nitrates. Each nitrate has a charge of -1 because that's the charge on nitrate. Over here, I have to take into account that there's a 2 out front here. So there's 2 potassium ions and there's 2 iodide ions. And I really should put AQ. Then what I'm going to do is I'm going to leave the solid intact in my ionic equation because those ions have come together to form the solid. I'm going to write this compound broken up into its respective ions because they are aqueous. So that product remains as aqueous. Then what I do to form what is referred to as a net ionic equation, I take each of those ions and I see which ones are common to each side of the equation. And what I do is I cross them off. These are called spectator ions. So I have 2 potassium ions. What else is common? 2 nitrate ions. Those get canceled out. And what you are left with are the ions that form the precipitate. That is what your net ionic equation should show. The ions that end up creating your precipitate. Okay? And there we go. And we just want to double check that we've got 2 iodine, 2 here. 1 lead, 1 lead. This +2 charge, 2 minus charge, those balance out to have something that's neutral, which you have on the right-hand side. So remember that K plus and NO3, just so you know, and I'll just write those up here, those are called spectator ions. They are not the ones involved in the making of the precipitate. Our next example is silver nitrate and potassium chromate. When we are predicting the products for this particular one, what I would like to do is I would like to take a look at the balanced equation first. So let's go ahead and do that. So here I have silver nitrate. Silver has a charge of +1. Nitrate has a charge of -1. Crisscross, you get AgNO3. Then we have potassium chromate. Potassium has a charge of +1. Chromate is a polyatomic ion. You might have to look that one up. Has a charge of -2. When you crisscross, you get K2CrO4. So what ends up happening in solution, got silver nitrate and potassium chromate. Those ions are all mobile now once they are in solution. Then what happens is when they come together, we have all of these ions, and certain ions can start to hook up. Remember that the positive ion of the first compound hooks up with the anion of the second compound. And we see that we get silver chromate, and we also get potassium nitrate. One of these is the precipitate. How do we know? What we're going to do is we're going to go consult our solubility table. And on our solubility table, we're going to see that silver chromate is in fact the solid, and potassium nitrate is the aqueous substance. Just so you know, anything that ends in nitrate is always aqueous. Okay? So this will start to precipitate out at the bottom of the beaker, and you're going to get Ag2CrO4 as your solid. Let's go take a look at what this reaction looks like in terms of a demonstration. Okay, now that we're back, we know that silver chromate is our solid, and we're going to just write that out to finish our word equation here. Silver chromate plus potassium nitrate. What I've done is I've gone ahead and I've balanced this equation. Remember that the one that is a solid, I put an S for solid. I leave the other product as aqueous. Then what you do is you take each of your reactants and you break them up into their respective ions, just as we saw in the beakers. We leave the solid intact as a product, and we still break up the other product into its ions. We must go make sure that we apply the coefficients to the ions as well. So because there were 2 silver nitrates here, that means you have 2 silver ions and 2 nitrate ions. Here, there was a subscript of 2 for potassium, so that means you must put a 2 here. Okay, this one is like that. This 2 means you apply it to potassium and to nitrate. Put a 2 and a 2. Now what we do is we go ahead and we cross off what's common to both sides. So we have 2 potassiums, we have 2 nitrates, and what we should be left with is what is referred to as your net ionic equation, the ions that make up your precipitate. So in this case, you have 2 silver ions coming together with 1 chromate ion in its aqueous form to form solid silver chromate. Okay, and when we do that, we can see that everything is balanced. In our next example, and this is our last example for double displacement reactions that form precipitates, okay, what we can do is we can take a look outside hookup, inside hookup. So magnesium sulfate and sodium hydroxide. When we have this written in terms of its molecular formulas, outside hookup, inside hookup. So what we end up getting is magnesium hydroxide and sodium sulfate. So let's write that down. Magnesium hydroxide plus, I know I'm running out of space here, sodium sulfate. Okay, So what I did was I did outside, inside, and I have created those compounds. Again, valence on magnesium is +2, sulfate is -2. I have to look at my polyatomic chart. I dropped the brackets because a 2 and outside the bracket was a 2, so the common factor there was 2, so I can do that. Sodium hydroxide, sodium is a +1. Hydroxide is polyatomic, it's a -1. Crisscross, I can drop the brackets. Magnesium hydroxide, magnesium is a +2, hydroxide is a -1. I must put brackets around the hydroxide, okay, and the 2 comes outside of that bracket. And I also get sodium sulfate. Which of these is the precipitate? Well, let's take a look. It's either going to be magnesium hydroxide or sodium sulfate. Let's take a look at sodium sulfate. Here's sodium, and I go across. Here's sulfate. That is aqueous. So that remains in solution. It is not your precipitate. The other option was magnesium hydroxide. Let's take a look. Here's magnesium. Here's hydroxide. You go until you meet. There's your solid. So that means that magnesium hydroxide is your precipitate. Let's go take a look at this reaction as a demonstration.
All right, what we have here are 2 beakers, each containing a dissolved aqueous ionic compound. In the beaker on the left, we've got magnesium sulfate. You can see that that is a clear and colorless solution. Looks just like water on first glance. And over on the right, we've got sodium hydroxide, which is also clear and colorless. Again, looks just like water. And what we're going to do here is we're going to mix these two and see what happens. You can see a white cloudiness forming right away, and what that cloudiness actually is the product of this reaction is actually a solid produced, and it's called a precipitate. And these very small particles that are suspended in that right now, but if we let this settle out over time, we'd find that they collect in the bottom as a solid.
Okay, now that we're back, we know that this is our solid and this remains aqueous. What we're going to do is we're going to break up our reactants into their respective ions. We're going to leave the solid intact, and we're going to break this product up into its aqueous form as well in our ionic equation. So here we have it. We have all of the ions listed for magnesium sulfate, sodium hydroxide. There's a 2 here, so you must put a 2 in front of that ion and a 2 in front of this ion. You have magnesium hydroxide, that stays as it is. And sodium sulfate, we had a 2 in front of this sodium ion because it has a subscript of 2, and then just sulfate. What we do now is we cross off our spectator ions, the ones that are common to both sides. They will not be responsible for the making of the precipitate. We see that sulfate gets canceled off. And you are indeed left with your net ionic equation, Mg +2 plus 2OH ions, yielding your precipitate of magnesium hydroxide. So this is a little bit more advanced than what you did in grade 10 in terms of just recognizing double displacement reactions. What you now need to be able to do is write a word equation for a double displacement reaction, a molecular, an ionic, and a net ionic. And these are for double displacement reactions that create precipitates.